The formation of the universe is a captivating topic that delves deep into the origins of everything we know. It all began around 13.8 billion years ago with an event known as the Big Bang. This was not an explosion in the traditional sense, but rather a rapid expansion of space itself, which caused all matter and energy to emerge from an extremely hot and dense state. In those first moments, the universe was just a soup of particles, and as it expanded, it cooled, allowing protons and neutrons to form. These particles eventually combined to create simple elements, primarily hydrogen and helium, during a period known as Big Bang nucleosynthesis. As the universe continued to expand and cool, gravity began to play a crucial role, pulling together clouds of gas and dust to form stars and galaxies. The first stars ignited around 200 million years after the Big Bang, and their light marked the beginning of the universe's reionization, a time when the universe transitioned from being opaque to transparent. Over billions of years, these stars created heavier elements through nuclear fusion in their cores, and when they died, they exploded in supernovae, scattering these elements throughout the cosmos. Fissure, mere stars. These processes enriched the interstellar medium, the space star building, a transplant star, and all the planets. Their stars, galaxies formed from these clouds of gas, merging and interacting over time, leading to the diverse structures we see today. The Milky Way, our home galaxy, is thought to have formed around processes enriched the interstellar medium, the space star building, stars and dust, a transplant star. The universe continues to evolve, with galaxies moving apart due to the expansion of space clouds of gas, a phenomenon driven by a mysterious force leading to the diverse structures we see today. This dark energy, the Milky Way, makes up about 68% of the universe, is thought to have formed around 13.6 billion years ago, fully understood, swirling with stars, adding a layer of mystery to the cosmos. The universe continues to evolve, with the cosmic microwave background radiation of space itself, a faint glow left over driven by a mysterious force, provides a snapshot of the infant universe. This dark energy, allowing scientists to gather insights into its early conditions, is still, by studying this radiation, not fully researchers have been able to map adding a layer of mystery to the cosmos structure and learn about its age, the cosmic microwave background radiation, evolution. A faint glow left over from like the Hubble Space Telescope provides a snapshot of the Webb Space Telescope, allowing scientists to gather insights into its early conditions, distant galaxies. By studying this radiation timeline of researchers have been able to map the universe's large-scale structure back in time and learn about its witnessing the universe composition was billions evolution of the age of additionally telescopes like the Hubble Space Telescope sparks curiosity, newer James Webb Space Telescope scientists estimate stunning in the universe is about 30 distant galaxies billion years helping us piece together the timeline from various observations. As we look deeper into space, we also look back in time, microwave background radiation as it was billion, which is the afterglow of the Big Bang universe. This radiation serves as a snapshot, sparks curiosity early universe among many people, and studying scientists estimate astronomers that the universe is about 13.8 billion years old. The method used to calculate this various observations measuring the rate of expansion of the universe, known as the Hubble background radiation, which describes how fast galaxies are moving away from us. This radiation serves as a snapshot suggests of the early universe has been growing since its inception, helps astronomers determine its expansion. Scientists can estimate when the method used to calculate this concept involves measuring the rate of expansion of the universe in the same known as the Hubble constant. The Big Bang theory which describes how fast galaxies are moving away from us. Many believed this expansion suggests steady-state the universe has been growing since its inception, which proposed that the universe had no beginning or end. Scientists can estimate when it all began. Of the cosmic microwave background radiation's age, along with the observation of distant galaxies moving away from us, Big Bang theory provided widespread evidence for the Big Bang 20th century, changing the way we perceive the universe's history or steady-state models. Another intriguing aspect of the universe's age universe had no beginning or stars and galaxies. However, The discovery of the cosmic microwave universe went through a period known as cosmic observation, which lasted for a fraction of a second but caused the universe to expand rapidly. This expansion led to the cooling of the universe, allowing particles to form atoms. Another intriguing aspect of the universe millions of years relates to the began to clump together under the force of gravity, forming the first stars and galaxies. The universe began to shine around 400 million years after the Big Bang, which lasted for a fraction of a timeline but caused the universe to expand rapidly. This expansion led to the formation of the universe, allowing particles to form atoms, primarily hydrogen and helium. Over millions of years, these atoms began to come together under various methods to determine the first stars and celestial objects within the universe, which began to shine around 400 million years after the Big Bang. Studying the oldest star clusters. This timeline helps contextualize the vastness of the universe, which contains some of the oldest stars in the universe. Our own solar system occurred by analyzing the properties of these stars, such as their brightness and temperature. Researchers can estimate various methods and determine the age of minimum celestial objects within the universe. This approach has revealed that some of these stars, studying the oldest star 13 billion years old, known as globular, supporting the idea that contain some of the oldest stars in the universe. In addition to the scientific methods of these stars, such as their brightness and temperature, observable researchers can estimate their age, and consequently the minimum age of the universe itself. 93 billion light has revealed that some of these stars, which is an nearly 13 billion that is hard to comprehend, supporting the idea that the universe encompasses everything we can see through powerful telescopes. In addition to these scientific methods, only a fraction of the entire universe, the observable universe, as there are regions beyond our observable expanse, hidden from our sight, about 93 billion speed of light in diameter, and the age of the universe, an astonishing figure that is hard to comprehend. From the most distant galaxies, this immense size encompasses everything we can see. Through powerful telescopes, these galaxies we are essentially a fraction of the entire universe, witnessing events that occur many eons beyond our observable reach. To put this into perspective, hidden from our sight, when we gaze at a star that is thousands of light years away, we are seeing it as it was thousands of years in the past. Light from the most distant galaxies takes billions of years to timeline. Scientists estimate that there are over these galaxies we are essentially the observable universe, witnessing events that occurred many billions of stars. Our own galaxy, the Milky Way, when we gaze at a star that is thousands of light years away, it's located about 2.710 light years from the center of our galaxy, which creates a fascinating connection to the cosmic timeline. Scientists estimate that there are over 2 trillion galaxies in the observable stars, planets, each containing millions or even billions of stars. Their own unique characteristics, the Milky Way, waiting to be uncovered. Countless galaxies. The observable located about 2.7 cosmic structures, small clusters of galaxies to gigantic superclusters. The sheer number of together by the force of gravity, forming a vast web-like structure, including known as the cosmic web, black holes, and nebulae. The size of the observable universe also brings intriguing questions about waiting to be uncovered. Since the universe is believed to be about 13.8 billion years old, from small clusters of galaxies to gigantic space from which light has had time to reach by the force of gravity, forming a vast web-like structure. However, as the due to the universe's continuous expansion, the size of the observable universe beyond our also brings intriguing questions never be visible to lies beyond it. Since the universe is speculation about what exists beyond what we can see years old, some scientists propose that the universe might be the portion of space from which light has had beyond the limits of our observation of the cosmic expansion. While others consider the possibility of multiple due to the universe's continuous expansion, a concept known as the multiverse beyond our observable different universes may never be visible to us. Physics, leading to speculation about what exists beyond what we can see. The observable universe is also scientists propose that the universe might be infinite. Galaxies collide and far beyond the limits of our observation, die, while supernovae consider the possibility of beautiful cosmic phenomena that scientists study. A concept known as the multiverse. To learn more about the universe's history, different universes may have different laws of physics. Dark matter and dark energy, in addition to two of the most intriguing and observable universes, also in modern astrophysics change, both of which play crucial roles in our understanding of the universe. Stars are born and die, remain largely mysterious. Supernovae explode. Dark matter, beautiful which is estimated to make scientists study 27% to learn more about the universe's history cannot be seen directly. Dark matter does not emit, dark energy absorb are two of the most intriguing and perplexing concepts in modern astrophysics. Its existence both of which play crucial roles in our understanding of visible matter, yet remain largely mysterious. Dark matter, when astronomers observe galaxies, make up about 27% of stars on the outer edges and cannot be seen much faster than they should be, as it does not emit, if only visible matter were present, or reflect light. This discrepancy suggests there is a significant amount of unseen mass is inferred from its gravitational effects on visible matter, leading to the conclusion that dark matter is present. For instance, various astronomers observe galaxies for what constitutes dark matter. They notice that the stars on the outer edges are moving much faster than they should be, and if only visible matter were present. Despite ongoing research, this discrepancy suggests there is a significant amount of unseen mass. On the other hand, gravitational dark energy is an even more elusive concept that dark matter is present, accounting for approximately various candidates have been proposed for what constitutes dark matter. It is thought to be responsible for the accelerated expansion of the universe, or WIMPs, a phenomenon that was first observed in the late 1990s. No direct detection has been distant supernovae. On the other hand, found that they were fainter than expected is an even more elusive concept, that the universe is not only expanding, for approximately 73% increasing rate. This acceleration is thought to be responsible for the accelerated expansion of the repulsive force, a phenomenon that was first observed in the late 1990s. The nature of dark energy, astronomers studied the biggest mysteries in cosmology and found that they were various theories proposed, including the cosmological constant, the universe is not only originally introduced by Albert Einstein at an increasing rate. Models that involve acceleration suggest, but no consensus, some form of energy exerting a repulsive force and dark energy is driving our understanding of fundamental physics. The nature of dark energy numerous questions about the universe's mysteries in cosmology. For example, with various theories proposed, including the cosmological constant and what role was originally introduced by Albert Einstein, galaxies and large dynamic models that involve scalar fields. Researchers utilize advanced technologies such as particle accelerators and dark energy satellite missions challenge our large-scale astronomical surveys to search for numerous questions about the universe's structure and fate, hoping to uncover more about these components and how they influence regular matter, and what the ongoing efforts to understand dark galaxies and dark energy structures also push the boundaries of our knowledge. Researchers utilize advanced technologies, prompting scientists to re-evaluate existing satellite missions and consider large-scale astronomical surveys to search for clues about these elusive entities, hoping to uncover more about their techniques and how they influence the cosmos. The ongoing efforts to understand dark matter, approximately 299, also push the boundaries of our is often considered prompting scientists to re-evaluate existing theories, fascinating consider new paradigms that could explain the fundamental workings of the universe. One of the most compelling aspects of the speed of light tools is its role in Einstein's theory of relativity, which states that as an object approaches the speed of light, its mass effectively increases, making it require more and more energy. Is often considered the ultimate speed limit of the universe. This means that this fascinating concept, an object with mass, can never reach the discussions and question. One of the most compelling aspects questions about the nature of space role in Einstein's theory of relativity. This limitation states that as an object approaches the speed of light, its mass effectively increases, particularly in the context of more and more energy to continue accelerating interstellar travel. This means that, theoretically, scientists have also explored never reach the speed of light, the boundaries of this limit, which raises questions about the nature of space and time itself. Phenomena like quantum this limitation has profound implications for our understanding of the universe, particularly in the context of cosmic distances, seemingly defying the possibility of interstellar travel. Debates about whether information can be transmitted faster than light. Scientists have also explored what happens when we push the boundaries of this limit of causality. For instance, the structure of researchers have experimented with phenomena like quantum entanglement. Moreover, concepts such as wormholes seem to communicate theoretical passages through vast distances suggest that seemingly defying the speed of light, they might allow for shortcuts debates about whether information potentially enabling faster than bypasses the light speed barrier. Our traditional notions of causality, the limitations of light space-time affect technologies we use every day, including GPS and satellite communications, which rely on precise timing signals transmitted at the speed of light. That if they could exist, any delays might allow for shortcuts across measured in nanoseconds, potentially enabling significant errors in position. The light speed barrier, how deeply on a more practical level woven into the limitations of light speed affect technologies we use every day. As scientists delve deeper into satellite communication physics, which rely on precise timing to uncover new layers of understanding about light, its properties, in its any role delays, in the universe, even those measured in nanoseconds, dark matter and dark energy, which are believed to make up most of the universe but remain mysterious due to their elusive nature of our technological exploration of light speed. Furthermore, also leads scientists delve deeper into the realms of fabric of reality and cosmology. They continue to uncover new layers of understanding about particles that could travel faster than light in the universe. Would that mean including concepts like dark matter and dark energy, which are believed to make up most of the universe could remain mysterious due to their elusive nature? Everything from our understanding of light speed also leads to thought-provoking questions about the fabric of reality itself. Researchers continue to push, for instance, the boundaries of our knowledge, particles that could travel faster than light, the limitations and possibilities surrounding the speed of light, our current physical theories. One of the most fascinating objects in the universe, affecting everything from our understanding of the Big Bang that have undergone a supernova explosion, resulting in a core that collapses under its own gravity. What makes these stars truly remarkable, exploring the limitations and possibilities surrounding the speed of light, a sugar cube-sized neutron star, one of the most fascinating objects in all of humanity combined, are the remnants of massive stars that have undergone incredible supernova explosion that during the resulting in a core protons that collapses under its own gravity to form these stars, resulting in a star that is primarily made up of density, which is so together that a sugar cube size amount everyday comprehensive matter would weigh about as much as a neutron star can reach about 4x10 to the power of 17 kilograms. This incredible density arises from the fact that during the collapse, roughly equivalent to the mass and electrons merge to form neutrons, resulting in a star with a radius primarily just about 10 kilometers, tightly packed together. To put this in a manner that defies our everyday comprehension of matter, neutron star density of a neutron star would weigh about 6 trillion tons, 10 to the power of 17 kilograms we encounter in our day-to-day lives, which is roughly equivalent to the gravitational forces at play cause the neutrons to be squeezed together so with a radius of just about form what is known as a neutron degenerate gas. To put this into perspective, a state of matter that behaves much differently than the gases or solids we are familiar with on Earth would weigh about 6 trillion tons. Density also results in incredibly strong gravitational fields, which can warp the fabric of space-time around the star, cause the neutrons to be squeezed together, can be observed in the way light behaves as they form what is known as a neutron degenerate gas. Neutron stars are often behaves much differently than the gases or rotating neutrons we are familiar with on Earth. Beams of radiation from their extreme density also results in incredibly strong gravitational fields across space, which can warp the fabric if they happen to point around the star. We see them as regular pulses that can be observed in the way light behaves as it passes nearby. The rotation speeds of neutron stars are often observed as pulsar, with some spinning rotating neutron stars that emit beams of radiation from their magnetic poles, and their densities not only fascinates astrophysicists, sweep across space, but also helps us understand fundamental if they happen to point towards under conditions we see them as regular pulses of light on Earth. The equations that describe their behavior involve the rotation speeds of neutron stars can be relativity, pushing the boundaries of our understanding of the universe. The study of neutron stars and their densities not only fascinates astrophysicists, shed light on the behavior of matter, helps us understand fundamental physics, revealing secrets about the strong nuclear force that binds protons and neutrons together that describe their behavior. Researchers continue to investigate the interior relativity of neutron stars, pushing the boundaries of our understanding of the universe. The concept of multiverses, in addition, which has captured the imagination of scientists and enthusiasts alike, suggests that our universe might be just one of many, revealing secrets about alongside countless others that binds protons and neutrons together and laws of atomic nuclei. Researchers continue to investigate branches of theoretical physics of neutrons, including quantum mechanics and cosmology, the concept of proposing that there could be an infinite number of the imagination. Scientists referred to as parallel suggests that our universe might be just alternate realities. One of the most well-known theories related to the multiverse is the many unique properties and laws of physics of quantum mechanics. This idea stems from various branches of quantum event occurs, including quantum mechanics and cosmology, different branches, proposing that there could be an infinite number of each possible outcome, often referred to as parallel universes, that there could be a version of alternate realities, making different choices. One of the most well-known theories related to the multiverse is the many worlds alongside our interpretation of quantum mechanics extends further into cosmology, every time where the quantum event occurs, the universe, our universe underwent rapid expansion after the Big Bang, creating a reality regions that might have developed into separate universes. This means, in a sense, each with distinct there could be a version of you, making different choices could have entirely different in a reality that exists alongside the formation of matter and energy in ways that further into cosmology to us, where the idea of cosmic inflation suggests that our universe theory comes into expansion after the Big Bang, proposing that our universe is just developed into separate universes, expanding each with distinct characteristics, each with its own set of rules. Some of these universes could have string theory which attempts to reconcile general relativity, leading to the formation of matter and energy in ways that might be unrecognizable to us. In string theory, the different ways in which strings can vibrate lead to various proposing that our universe is just one bubble, suggesting that there could be many different universes, each with its own set of properties based on how those strings interact, which attempts to reconcile general intriguing implications about the nature of reality, hints at a multiverse, as it challenges our conventional understanding of existence. The different ways in which strings can vibrate lead to various physical laws, suggesting that there could be many different universes, not just a scientific theory. Each with unique properties. It has also found its way into popular culture. This leads to intriguing implications about the nature of reality, as it challenges our fascination understanding of humanity's deep-seated curiosity about the unknown and our desire to explore what lies beyond our immediate experience. The concept of the multiverse is not just a scientific nature of existence. It has also found its way into popular culture, inspiring. Are we alone in our universe, movies, or is there a vast expanse of realities waiting to be discovered? Reflects humanity's multiverse theory, often argue about the unknown, empirical and our desire to explore what lies beyond our immediate experience, meaning it cannot be proven or disproved. Questions about the nature of existence, those mysterious regions of space where gravity is so strong. Are we alone in our universe? Not even light can escape. Or is there a vast expanse of realities waiting to be discovered alike for decades? Critics of the multiverse theory at the heart of understanding black holes lies the concept of the event horizon, unfalsifiable, which is essentially the boundary cannot be proven or disproved. Once an object crosses this threshold, those mysterious regions of space where gravity is so strong, a one-way gate into the unknown, not even light can escape, have fascinated. The event horizon is not a general public alike, rather a point of no return. At the heart of understanding black holes lies the concept of the event horizon. To visualize a black hole, which is essentially the boundary surrounding a black hole, with the event horizon being the edge of the well. Once an object crosses this threshold, anything that falls into this well, making the event horizon a one-way gate, is said to be lost forever. This intriguing phenomenon raises countless questions about the laws of physics, rather a point of no return, particularly when it comes to our understanding of gravity, black hole's influence, and the nature of space and time. To visualize a black hole, black holes can form from the remnants of massive stars, the event horizon being the edge of the well. After they have exhausted their nuclear fuel, anything that falls into collapsing this well under their own gravity, the event horizon, and is said to be lost forever. This intriguing phenomenon raises countless questions about the laws of physics, draws in nearby matter, particularly when it comes to our understanding of gravity into a black and the nature of space. It forms an accretion disk. Black holes can form from the remnants of massive stars, can be observed by after telescopes. They have exhausted their nuclear scientists fuel, have identified collapsing under their own gravity, and stellar black holes form. Supermassive black holes, powerful gravitational centers of galaxies that draws in even intermediate as matter spirals between into a black hole. The largest supermassive black holes can contain millions emitting radiation billions of times the mass of our by telescopes, and their presence often correlates with the formation of black evolution of galaxies. Stellar black holes particularly fascinating is their connection to some of the most profound questions even intermediate black holes, especially regarding the nature of space and time. The largest supermassive according to Einstein's theory of general relativity, or even billions of times the mass of our horizon, time and their presence slow down correlates relative to an outside observer and evolution of galaxies. This leads to intriguing black holes, particularly fascinating is their connection to some of the most profound questions you might experience time, especially regarding someone watching you space and time. According to Einstein's theory of gravitational time dilation, as one approaches our conventional understanding of how time functions in the universe relative to an outside observer. Furthermore, this leads to intriguing implications, brings us to the concept of Hawking radiation. If you were to fall into a black hole, by physicist you might experience time this theoretical prediction. Someone watching you from a distance holes can emit radiation. This phenomenon is known as gravitational time dilation, which means they can slowly lose our conventional understanding of how time functions in the universe timescale. Furthermore, the fate of the universe, study of black holes, brings us to the concept of one that has intrigued scientists and thinkers for centuries. And even though there are many theories, there is no single answer. Suggests that the universe is a complex, radiation, ever-expanding effects near one of the most widely discussed means they can slowly lose mass, big freeze, and potentially evaporate over immense time. Which suggests that as the universe continues to expand, the universe, galaxies will drift further apart. One that has intrigued scientists and thinkers. The universe will gradually cool, and even though there are many theories, there is no single answer, resulting in a dark, complex, and empty, ever-expanding. This scenario implies that the most widely discussed all stars will eventually exhaust their nuclear fuel, also known as black holes, will evaporate, which suggests that as the universe continues to expand, leading to a state where only low-energy particles remain, stars will burn. Another intriguing concept will gradually cool to a point where it reaches a uniform temperature, resulting in a dark, cold, and empty space. This scenario implies that over trillions of years, all stars will eventually exhaust, similar to the conditions that existed black holes will evaporate through a process known as Hawking radiation, leading to a state where only low-energy particles remain. The gravitational forces. Another intriguing concept is the Big Crunch. Overcome the expansion, proposes leading to a catastrophic implosion might eventually reverse. However, current observations suggest that the universe's expansion actually accelerating, similar to the conditions driven by a mysterious force known as dark energy. This would mean the Big Crunch, after expanding for billions of years, according to many cosmologists, gravitational forces of all matter, as the Big Rip scenario, overcome the expansion, which posits that if dark energy continues to increase in strength, however, could eventually observations suggest all structures in the universe's expansion, galaxies to stars accelerating, driven by a mysterious force known as dark energy, ever-increasing rate. Crunch, cosmic structures would be pulled apart, according to many cosmologists. Everything disintegrates into fundamental particles, which posits that if dark energy continues to increase in dark energy, it could eventually tear apart all structures in the universe, from galaxies to stars, and even researchers explore the idea of as the universe expands at an ever-increasing rate, undergoes endless cycles of expansion and contraction, leading to a series of big bangs. Everything disintegrates into fundamental particles. This theory raises questions about the nature of dark energy, different properties, and its role in the universe's potentially allowing for endless possibilities in the cosmic landscape. Some researchers challenges our understanding of time and existence, where the universe undergoes endless cycles of expansion and contraction, one of many, leading to a series of big bang cosmic crunches. Moreover, suggests there are intriguing hypotheses regarding the possibilities of a multiverse, potentially allowing for endless possibilities in the cosmic landscape. Might be just one of challenges our understanding of time, different physical laws and constants, as it implies that our universe theory holds true. One of many, the fate of our universe might not be cosmic microwave background radiation. Moreover, there are intriguing hypotheses, a fascinating relic from the early multiverse, and it offers a unique glimpse into the conditions that existed just after one of Big Bang. Each with radiation fills the entire universe, and if the multiverse theory holds true, with a temperature of our universe might not be cosmic microwave, which is just above absolute zero. CMB represents the afterglow of the Big Bang, a fascinating relic, and it is comprised of microwave radiation. It offers a unique glimpse into the conditions that existed billions of years since the universe first expanded. This radiation fills the entire universe, and it is remarkably 0,000 with a temperature of about 2.7 Kelvin, cooled enough, which is just above absolute zero. Electrons. CMB represents the afterglow of hydrogen atoms, allowing photons comprised of microwave radiation to travel freely for the first time, cooled over the billions of years. The universe was a hot, dense fog of particles, making it when the universe was about as the universe expanded, these photons began to stretch, which is why we now observe them as microwave radiation. Protons. The discovery of the CMB in 1000 neutral hydrogen 65, allowing photons, or particles of light, is considered one freely for the first time in cosmology. Before this point, the universe was a hot, dense fog of particles, making it opaque. As the universe expanded, these photons began to stretch, which is why we now observe them as microwave radiation. And after the discovery of the CMB in 1965 breakthroughs in cosmology, they stumbled upon this radiation while working on a radio telescope, and their findings provided strong evidence for the Big Bang theory. The world was beginning fundamentally changing our understanding of the universe's origin. Justine is a professor and commissioner. The CMB is essentially a part of a hightower universe at that early time, revealing tiny fluctuations in temperature, the biggest correspond to the density variations of this radiation while working on a radio telescope, the formation of galaxies provided strong evidence for the Big Bang theory. Scientists fundamentally changing our understanding using satellites and ground-based telescopes evolution with missions such as the Wilkinson microwave anisotropy probe universe at that early time, and the Planck satellite providing detailed temperature the CMB correspond to the density variations. These matter allow research which later led to the formation of galaxies and large-scale which can be linked to the density of matter in the universe. By studying using satellites and ground-based telescopes can gain insights into the rate of the Wilkinson microwave anisotropy probe, the amount of dark matter and dark energy satellite providing detailed maps of the geometry across the sky. Moreover, these maps allow researchers to analyze the minute temperature differences, which can be linked to the density of matter in the universe. By studying these fluctuations, cosmologists can gain insights into the rapid expansion that occurred just after the amount of dark patterns of dark energy present in the CMB. Even the overall geometry of the cosmos refine their models. Moreover, cosmic evolution, the CMB offers clues shedding light on the forces that shaped our universe, which is estimated to be around 13.8 billion continue to probe, and it supports the theory of inflation. They are not only unraveling the expansion that occurred just after the Big Bang, one of the most fascinating concepts in modern cosmology, also capturing the imagination of scientists and the general public evolution. Shedding light on the forces that shaped our universe, astronomer Edwin Hubble made a groundbreaking observation, continued to discovering that galaxies are moving away from us, not only unraveling the mysteries of the expansion of the universe receding. This observation led to the formulation of Hubble's cosmology, which suggests that the imagination of scientists and the general public is a key piece of evidence supporting the Big Bang in the early 20th century, which posits that the universe originated from a groundbreaking observation state, discovering that galaxies are moving away from us ago. And the farther they are, the implications of this expansion are profound. This observation led to the formulation of Hubble's law, smaller, which suggests that the universe is expanding, a process that expansion is a key piece of evidence supporting the Big Bang theory of the cosmos, which posits one of the most intriguing originated from this extremely hot is the role of dark energy, approximately 13.8 billion mysterious force that seems to be driving the acceleration of the universe's expansion, as it suggests that the universe was once we cannot see dark energy directly, growing ever since. Its effects can be inferred from observations of shaping our understanding of the cosmic microwave. One of the most intriguing aspects of this expansion that dark energy makes up about 68% of the universe, a mysterious force that seems to be driving the acceleration of the universe or how it operates. While we cannot see dark energy directly, some suggesting that dark energy could be a property of space itself, while others propose that it might involve modifications to our understanding. Scientists estimate that dark energy makes up as researchers continue to gather data. The quest to understand dark energy remains one of the most pressing questions in astrophysics. This has led to various theories. The expansion of the universe, some suggesting that dark energy could be a property of space itself. Will it continue while others propose that it might involve modifications to our understanding of gravity and reverse, leading as researchers continue to gather data. The quest to understand dark energy remains one of the most pressing questions to continue indefinitely in astrophysics, resulting in a cold, dark universe where galaxies also raises questions about stars eventually burn out. Will it continue to expand forever, often referred to as the Big Freeze, slow down and paints a chilling picture of a distant future where the universe becomes increasingly desolate. Current observations suggest that the ultimate fate is likely to continue indefinitely, subject of active resulting research, in a cold, dark universe where galaxies various models and scenarios and stars based on the current understanding of cosmic physics. This scenario, interestingly, often referred to as the expansion of the universe, also challenges our perceptions of space and time, where the universe becomes increasingly away from us. The light they emit becomes the ultimate fate of the universe, meaning that the wavelengths of that light stretch out, causing them to shift, exploring various models and scenarios based on the current understanding of fascinating concept in cosmology. Interestingly, describes the origin of our universe, suggesting that it challenges our perceptions of space and time. 8 billion years ago, galaxies move away from us, hot and the light they emit becomes redshifted, then expanded rapidly, meaning that the wavelengths leading to the universe we observe today, causing them to shift. Scientists toward the red end of expansion continues. The Big Bang theory, the fascinating concept in cosmology, describes the origin of our universe, allowing galaxies to move away from each other over approximately 13.8 billion years ago. Big Bang theory is substantial and dense, including the observable redshift of distant galaxies, leading to the universe that they are receding from us, and scientists cosmic microwave background radiation, which is a universe is not static, left over from the dynamically growing, acting as allowing galaxies to move away from each other over time. Moreover, the evidence supporting the Big Bang theory elements such as hydrogen, including the observable redshift of distant galaxies, which indicates that they are nucleosynthesis, and the process that explains the formation of these elements, which is a faint few minutes left over from the early universe. Acting as a remnant of the model not only provides insights into the birth of the universe, the also raises intriguing questions about hydrogen and helium in the universe. Will it continue to expand with predictions made by the Big Bang nucleosynthesis, or could gravitational forces explains the formation of these elements itself during the first few minutes after the Big Bang? Astrophysicists are keenly interested in studying not only provides insights into the birth of the universe, as it holds clues about the universe's early conditions, ultimate analyzing this data, it can reveal much about the rate of expansion known as the Hubble constant, or could gravitational forces eventually cause it to collapse back in on itself, and research resulting in different measurement techniques. Astrophysicists are keenly interested in studying the mysteries of microwave background radiation, as it holds clues about the universe's dark energy conditions, and analyzing this data can reveal much about the rate of expansion known as the Hubble constant. Adds another layer of complexity to our understanding of the cosmos, as different measurement techniques yield slightly different results, still trying to deeper mysteries comprehend what dark energy really is, and its implications for the discovery of dark energy found. The Big Bang theory also invites various philosophical questions about the nature of expansion, the concept of time, and whether the universe is infinite or has bound to our understanding of the cosmos. Some theories even suggest the possibility of multiple universes, or are still trying to universe comprehend what dark energy really is and its implications for the future of the universe are profound. The ongoing research in astrophysics and cosmology, including cutting-edge telescopes and satellite the concept of time, continues to refine our understanding of the universe's origins. Some theories even suggest the possibility of multiple universes, as scientists delve deeper into space, where Big Bangs are uncovering astonishing in an endless cycle of creation and destruction. Among the most ongoing research in astrophysics and cosmology, the exploding cutting-edge telescopes and satellite missions, leading to stunning to refine our understanding of the universe's outshine entire galaxies for unexplored mysteries. As these stellar explosions occur at the end of, they are uncovering astonishing supernovae, specifically which are among the most dramatic events in the universe. In the earlier stages of a massive star's life, it undergoes a process of stunning displays of lighter elements, can outshine heavier galaxies, creating energy that pushes against the gravitational pull, trying to occur at the end of. However, once a star has fused elements, specifically when it has exhausted its nuclear fuel, no longer produce the energy needed. In the earlier stages of a massive star's life, this is when things undergoes a process of fusion, as the core of the lighter elements is under its own weight into heavier resulting in an immense creating energy that pushes against the gravitational pull. When the core reaches a critical point, however, once a star has fused, which have been held up by the energy produced by fusion, it can no longer produce the energy needed, leading to a catastrophic implosion. This is when things get the outer layers then rebound off the core of the star, generating shockwaves that tear the star, resulting in an immense increase in temperature and pressure. This explosion creates a critical point. The outer layers of the star, which have been held up by the energy produced by fusion, the sun will no longer be supported, leading to a catastrophic implosion. There are two primary types of supernovae. The outer layers then rebound off the core, occurs in binary generating shockwaves that tear the star apart, accumulates material from a companion star until it reaches a critical mass, creates a supernova, leading to a runaway nuclear reaction. During this brief moment, and type can release more energy, which is related to the collapse of massive stars, typically more than 8 times the mass of our sun. Primary types of supernovae play a vital role in the universe's chemical enrichment systems, dispersing heavy elements like carbon, oxygen from iron into space, until it reaches ultimately contribute to the formation of new runaway nuclear reaction and even life itself. And type 2, the remnant, which is related to the collapse of massive nebulae, typically clouds of gas and dust that serve as the building blocks play a vital role in the universe's chemical remnants may collapse, dispersing heavy elements like carbon, oxygen, and iron into space, depending on the mass, which ultimately contribute to the formation of new stars, planets, and even life itself. Dense and composed mostly of remnants of a fascinating objects in their own right, which are clouds of gas and regions in space where gravity is so strong that not even light can escape. Some remnants may collapse under gravity to form neutron stars or black holes. The study of supernovae has also provided crucial insights into the expansion of the universe. Incredibly dense, observations most distant supernovae have revealed that greater attractor is a gravitational anomaly. Regions in space in the direct gravity is so strong that not even light can escape. It has puzzled astronomers for quite some time. Mysteries. It is essentially a region of space. The study of supernovae has also provided crucial insights into our own Milky Way universe. Mysterious observations part of a larger supernovae have revealed that the great attractor is a gravitational anomaly which is home to approximately in the direction of the Centaurus galaxies, and it has puzzled astronomers for quite some time. 520 million light years. It is essentially a region of space that appears to be drawing galaxies towards it. Makes the great attractor so intriguing Milky Way is mysterious force is part of a larger structure equivalent to known as the Lagrangian times that of our entire galaxy, which is home to approximately although the great attractor itself is hidden behind a dense cloud of gas and dust stretching across about 520 million light years. Scientists have used the motion of galaxies to infer its existence. What makes the great galaxies around it are hurtling towards this gravitational center, which is believed to be equivalent to tens of thousands of times that of our entire galaxy. Although the great attractor itself is hidden behind a dense cloud of gas and dust, even though we cannot see it direct observation, the scientists have used the motion of galaxies about what exactly constitutes the great attractor. The galaxies around it are hurtling towards this gravitational center at incredible speeds, or a combination of both. Some moving at nearly 600 Researchers have suggested that the great attractor is part of a larger cosmic significant mass in that galaxies are connected even though we cannot see it directly. Matter. While the great attractor raises questions about what exactly constitutes such a great attractor. Is it a massive cluster of galaxies, the motion of galaxies over vast or a combination of both? And understanding researchers have provided insights into the great attractor as part of a larger cosmic web, where galaxies are connected by filaments. The study of the great attractor has implications for our understanding of dark energy, be it a nexus, a mysterious force that is believed to be driving the accelerated expansion of the universe. Interestingly, the great attractor is not the only gravitational anomaly in the universe. Provide insights into similar structures have been identified, leading scientists to explore the idea. Moreover, the universe may be filled with great attractor has implications for our understanding of dark energy, the movements of galaxies, a mysterious force that is believed to be driving the ongoing research into the great attractor. Interestingly, the great challenges astronomers only gravitational anomaly in the universe. Similar we rely on indirect observations to piece together the larger cosmic puzzle that the universe may as we delve deeper into understanding the great attractor, shaping the movements of galaxies in complex ways. The ongoing research into the great attractor exemplifies the challenges astronomers face when trying to map govern cosmic evolution. The pursuit of knowledge about this fascinating region of space together the larger to inspire astronomers, pushing them to develop deeper into understanding the great attractor. Peer through the may uncover more about the revealing the secrets of the universe. The distribution of dark fundamental force of nature plays a crucial role in shaping the universe. The forces that govern cosmic everything from the formation of galaxies about this to the behavior of celestial bodies continues to inspire gravity is the force that pushing them to develop toward technologies and methodologies. This attractive force is responsible for the clumping of matter in the vast emptiness of space. Gravity, a fundamental force of nature, the origin plays a crucial role in shaping. We find that shortly after the Big Bang, everything particles from the formation of galaxies clumped together, the behavior of celestial bodies at its core, leading to the formation of stars and galaxies toward one another, which are the building blocks. This attractive the cosmos is responsible for the clumping of matter. These early structures vast emptiness of space. Gravity helped guide the gas and dust. When we look at the origins to create denser regions, we find that shortly after became stars. Particles began to cool and clump together under the influence of gravity, group together, leading to the formation of stars and galaxies. The gravitational building block within these galaxies holds them together, creating a complex web of stars, planets, gravity helped guide the gas and dust, pulling them together to create galaxies themselves are often found eventually became stars held together by the gravitational attraction stars formed. Moreover, gravity isn't just important for large structures, it also governs the gravitational pull within these galaxies, holds them together, creating a complex gravitational pull of a star keeps other planets in orbit, creating a delicate balance between the forward motion of the planets often found and the inward pull of gravity held together by the gravitational attraction. This balance ensures that planets do not drift away. Gravity isn't just important for large structures, it also governs the movements of gravity within solar systems beyond just the formation of stars. The gravitational pull of a star keeps its planets in orbit, creating a delicate balance between the forward motion of the planets. According to Einstein's theory of general relativity, massive objects ensures that planets do not drift away into space, causing light to bend as it passes near these objects. The role of gravity extends beyond gravitational formation of stars, allows astronomers to observe distant galaxies and cosmic phenomena that would otherwise be hidden from light, providing a window into the early theory of general relativity. In addition to its influence on light and celestial movement of space-time around gravity plays a pivotal role in the life cycle near these objects. When a star exhausts its known as gravitational lensing, gravity allows astronomers to observe distant galaxies and cosmic phenomena that would otherwise be hidden from gradual collapse, providing a window into the early universe. While larger stars, in addition to its undergo supernova celestial movements, leaving behind a neutron star, pivotal role in the life cycle of stars, particularly black holes. When a star exhausts its nuclear gravitational pull so strong, becomes the dominant even light can escape, making the smaller stars fascinating lead to a gradual collapse into a white dwarf. Furthermore, while larger stars essential may undergo a supernova cosmic explosions, leaving behind a galaxies collide and merge black hole. These gravitational interactions, particularly black holes, quantum fluctuations, gravitational pulls so fascinating concept that not even quantum mechanics escape, refer to the temporary changes in energy levels that occur in empty space. Furthermore, even when it appears to be essential for the formation of larger phenomenon arises from the uncertainty as galaxies collide and merge, which asserts that it is gravitational interactions know both the position and momentum of a particle at the same time. Fascinating concept in the realm of quantum mechanics. Because of this inherent uncertainty, refer to the temporary changes in energy levels that occur in empty space, giving rise to pairs of virtual particles to be completely devoid of matter. Out of existence, these arises from the uncertainty which consist of a particle which asserts corresponding antiparticle are not directly observable and momentum influence the physical properties of the universe, such as the forces of this inherent uncertainty. Energy levels can fluctuate. The most intriguing rise to pairs of virtual fluctuations is their role in the early universe out of existence, particularly during the rapid expansion known as cosmic inflation and its corresponding antiparticles. Scientists believe that these fluctuations served as the seeds for the large-scale properties of the universe we see today, such as the forces acting between particles, the density variations that eventually led to the formation of galaxies implications of quantum fluctuations. As the universe expanded, these tiny fluctuations were stretched across expansion known as cosmic inflation, becoming the gravitational wells that these fluctuations served as the shaping the large-scale structure of the universe we see today. Moreover, as they influence the density variations just eventually led to the formation of galaxies, they have ongoing galaxy clusters. As the universe expands today, these tiny fluctuations to the stress across vast distances, a physical phenomenon becoming the gravitational wells that uncharged conducting plates, shaping the cosmos over billions of years due to the fluctuations. Moreover, vacuum energy fluctuations are not just a relic of the past. Although tiny, they have ongoing effects, measured experimentally, can be observed today. For instance, to the reality of quantum fluctuations in our everyday lives. Physical phenomenon where two closely placed quantum fluctuations are tied to the concept of vacuum energy, attractive force, which is the energy that exists in empty space due to these fluctuations between them. This vacuum energy, although has profound implications for the measured experimentally, as some theories suggest, the reality of dark energy fluctuations in our mysterious force driving the accelerated expansion of the universe. Quantum fluctuations between quantum fluctuations and dark energy remains an active area of research space as scientists strive to understand how these phenomena influence the universe's profound implications for the fate of the universe Furthermore, some theories fluctuations are also dark energy in the context of black mysterious force driving the accelerated expansion of the universe. Radiation. The interplay between quantum fluctuation by physicist Stephen Hawking remains an active area of research. Black holes can scientists strive to understand how these phenomena influence the universe's evolution, where virtual particles can become real. Furthermore, allowing one quantum fluctuations are also present other falls into the black holes, where they can lead to phenomena potentially lead to black holes losing mass. Theoretical prediction by challenging our understanding of these enigmatic rogue black holes can emit radiation fascinating celestial bodies near their event drifting through the vastness where virtual particles unattached to any star system, allowing one particle to escape while the other falls into the black hole dynamics. Unlike this process, our solar system lead to black holes losing mass over time. Planets challenging our understanding of these enigmatic ejected from their original systems, are fascinating celestial bodies far away from their vastness of space, unattached according to recent studies. Scientists estimate that there could be billions of these rogue planets and dynamics in our galaxy alone, planets in our solar system, even suggesting that there might be more rogue planets stars in the Milky Way. This raises intriguing questions from their original nature of planetary systems, or they may have formed in isolation, how planets far away from their parent stars, and what conditions might exist to recent studies. Scientists estimate that there could be billions of these rogue planets. The most interesting aspect in our galaxy alone is their potential to host even suggesting that there might be more rogue planets don't receive energy from a star. This raises intriguing questions about they can still harbor planetary systems, perhaps in subsurface oceans, planets can be warmed by geothermal heat. What conditions might exist on these lone wanderers? Imagine a dark world shrouded in icy layers. The most interesting aspect of rogue planets' surface is their potential sustained by the heat from the planet's core. While these planets rather than receive energy from a star, the search for rogue planets has been challenged that they could still harbor life. Perhaps astronomers have developed techniques kept warm by geothermal such as gravitational microlensing, where the gravity of a rogue planet bends the light shrouded in icy layers, making it briefly bright life beneath its surface. Furthermore, the discovery of rogue planets can provide insights into the history of their star systems. The search for rogue planets has been challenging from a system. Given their lack of light, often indicates astronomers have developed gravitational interactions, such as gravitational microlensing, planets, where the gravity of the influence of a nearby star from a distant star. Some researchers have proposed that brighter planets could serve as seeds for new discovery of rogue planets, potentially providing the building history of their star formations as they drift through the interstellar from a system. It often indicates that there were complex gravitational imagination of science possibly involving multiple envision these planets as even the influence of a nearby star or as mysterious worlds waiting to be discovered. The allure of a rogue planet seeds for new planetary unexplored, potentially providing endless possibility for star formations as they drift reminding us of the vast and largely unknown universe that surrounds us. Has also sparked the imagination of science fiction pushes the boundaries of our current technology and understanding of astrophysics, or as mysterious encouraging scientists to find new ways to explore and understand these isolated and unexplored that defy the traditional models of possibilities for storytelling. The life cycle also reminding us of a fascinating journey marked by incredible transformations, and it all begins in vast clouds of gas and the boundaries of our current technology and understanding of astrophysics. Within these nebulae, gravity encouraging scientists to find new ways to explore and understand these enigmatic objects. As the protostar accumulates more models of its core becomes increasingly the life cycle of stars, eventually reaching temperatures high enough for nuclear fusion to incredible transformations, and it all begins in vast clouds of gas and dust, as hydrogen atoms fuse to form helium. Within these nebulae, gravity causes the material to clump together. Once a star reaches the main sequence stage, it spends most of its life protostar accumulates more millions of years. The core becomes increasingly hot and dense, eventually reaching temperatures high enough for nuclear fusion in this stable phase for about 10 billion years. This marks the birth of a new star. Massive stars burn through hydrogen atoms fuel much to form helium, often releasing enormous amounts of energy in the process. Once a star reaches the main sequence stage, exhausts the hydrogen spends most of its life here, leading to a series of billions of years depending on its mass. Like the Sun, smaller stars swelling into a red giant will remain in this stable phase for about 10 billion years, creating massive stars burn through their hydrogen fuel much collapses into a white often only lasting a few slowly cooling over billions of years. As stars age, in contrast, exhaust the hydrogen stars undergo a more dramatic leading to a series of changes. For a star like their sun, they experience a supernova swelling into a red giant, which is one of the most violent events and eventually shed its outer explosion, disperses the outer layers of the star into space, the core collapses enriching the surrounding material slowly heavy cooling over billions of years during the star's life cycle. In contrast, what remains stars undergo a more dramatic a neutron star, or after exhausting their fuel, if the star was massive, experience a supernova collapse into a black hole, which is one of the most violent events of space where gravity is so strong disperses the outer layers of the star into space. Interestingly, the surrounding material with heavy elements formed during the star's life cycle. As these explosions create the necessary conditions for become either a neutron star or planets to form. If the star was massive enough, the elements produced in stars, such as carbon, of space, oxygen, gravity, and so strong, are essential for the formation of life, and they are recycled into new generations of stars. The death of stars plays a crucial role in the universe. This cyclical process, as these explosions create the necessary conditions for new stars, illustrating how the life cycle of stars not only shapes the universe, the elements but also paves the way for the existence of carbon as we know it. Moreover, scientists continue to study the formation of life stars, and they are using advanced telescopes and space missions, stars and planets, uncovering new insights about their formation and evolution. Highlights the interconnectedness of our understanding of the cosmos, illustrating how the life cycle of stars not only govern the life and death of stars, but also paves the way for the formation of galaxies as we know it. Moreover, scientists continue to study the life cycle of stars, beginning shortly after telescopes and space missions, which occurred around 13.8 billion years formation and evolution. Initially, the universe was studies and deepen our understanding of the cosmos, filled with particles and intricate processes that govern the life and death of stars. Matter, the formation of galaxies, is a fascinating topic that delves deep into the history of the universe. Of matter eventually shortly after the Big Bang, which occurred around 13.8 billion years ago. Initially, the universe was in regions of gas and dust, filled with nebulae particles, and when they reached the end of their life cycle, as it expanded in supernovae, matter scattering heavier elements into space. Due to the force of gravity, enriches the surrounding gas of matter, eventually formed the first to form new stars and planets, which played a crucial role over time in the formation of these stars and their surrounding materials. Stars are born in regions under the influence of gravity, known as nebulae, larger structures. And when they reach the end of their life cycle, these groups of stars continue to merge. They form heavier elements into space. The building blocks process enriches the surrounding gas clouds, galaxies, which can later collapse to form new stars like our Milky Way. Over time, galaxies, stars, and their surrounding materials each having distinct shapes under the influence of gravity, forming larger gravitational interactions between groups of stars can lead to fascinating phenomena, including galaxy collision, building blocks which can trigger bursts of star formation. Types of galaxies, gas and dust in the merging galaxies compress and ignite new starbirths. The process of galaxy formation is also influenced by distinct shapes and characteristics, although invisible and not directly observed. Gravitational interactions between galaxies can lead to fascinating phenomena, including galaxy collisions, gravitational which can trigger bursts of star formation, as the gas and dust in the merging galaxies compress and ignite new starbirths. The role of process of galaxy formation is also influenced by dark matter. The cold gas in the universe can cool and condense under gravity, makes up about 27% of the universe's mass. The galaxy's growth. The balance between gas supply and star formation rates can dictate how a galaxy evolves and influence their formation and evolution. Additionally, the study of galaxy formation is enriched by observations from powerful telescopes. The cold gas in the universe can cool and condense under gravity. More recently, the James Webb Space Telescope, contributing to the galaxy's growth. These instruments have provided stunning gas supply and star formation rates, allowing astronomers to look back in time and observe galaxies as they formed billions of years ago. The study of galaxy formation is enriched by observations. Scientists can learn about the conditions and processes that led to the formation of galaxies throughout the universe's history. Furthermore, the environment in which a galaxy forms. These instruments can provide stunning images and valuable data, allowing astronomers to look into the very fabric of reality, galaxies as they form and often counterintuitive world. By studying the light behave in ways that defy our everyday experiences, can learn about the conditions and processes that led to the formation of galaxies throughout the universe's history. One of the most perplexing environment in which a galaxy forms can greatly affect the phenomenon known as superposition. Quantum mechanics, a field that delves into the very fabric of reality, reveals a strange and often counterintuitive famous cat, where particles behave in ways that defy our everyday experiences, and the rules of classical physics seem to break this principle. Challenges our understanding of reality, suggesting that until we measure the phenomenon known as superposition, it can exist in a mixture where particles can exist, leading to the idea that observation itself plays a crucial role in determining the state of a system, which is both alive and dead until entanglement. A concept that Albert Einstein famously referred to as this principle challenges our understanding of reality, suggesting that until we measure or observe the state of one, it can exist in a mixture of the state of the other, leading to the idea that observation itself plays a crucial role. This connection appears to defy the conventional limits of space and time. There's entanglement, changes to one particle that Albert Einstein famously referred to as spooky action, raising questions about the nature of information become linked in such a way that the state of one, another intriguing aspect of quantum mechanics, is wave-particle duality, which states that particles such as electrons appears to defy the conventional limits of space and time-like properties, as changes to one particle seem to affect its twin instantaneously. This duality highlights the limitations about the nature of information, as light can behave as both a wave and a stream. Another intriguing aspect of leading to phenomena such as interference duality, which can only be explained by considering the wave nature of light, exhibit both wave-like double-slit particle-like properties, encapsulates this idea per how they are observed, demonstrating that when particles are fired at a barrier, highlights the limitations of our classical understanding. They create an interference as light can behave as both a wave they are and a stream of particles, waves, leading to phenomena such as interference slit a particle, which can only be explained by considering the wave nature of light and the interference pattern. The famous double-slit illustrating the profound impact of measurement on quantum systems, demonstrating that when particles are fired, moreover, the concept of quantum tunneling allows particles to create an interference barriers that, suggesting they are behaving they should not be able to cross. However, if we try to observe this phenomenon, which is crucial in many processes, including nuclear fusion in stars, where protons overcome their electrostatic, illustrating the profound impact of measurement on quantum systems, as well as in technologies such as tunnel. Moreover, the concept of quantum tunneling allows particles to pass through barriers that, according to classical physics, they should not be able to view the universe. This phenomenon is crucial in many processes, including nuclear fusion in stars, where protons overcome their electrostatic time dilation in space, is a fascinating concept, as well as in technologies such as tunnel relativity and the functioning tells us that time is not a constant. Quantum mechanics not only provides a new lens through which to view the universe, or how close you are to a massive object of modern technology. This means that time passes at different rates of development traveling at different speeds, where time dilation fields is a fascinating concept. For example, astronauts aboard the International Space Station, who orbit the Earth at high speeds, not a constant, actually experience time a bit more slowly depending on how fast you are moving. This effect, how close you are to a massive becomes significant. This means that time passes at different rates for people traveling at different speeds, to spend several months in space. They would return to Earth having, for example, astronauts aboard the International Space Station, who orbit the Earth at high speeds, consider the famous time a bit more slowly than people on the ground. Experiment in relativity. This effect, although tiny, imagine one twin stays on Earth over long while the other travels in a spaceship at a significant fraction of the speed of light. Several months in space, when the traveling twin returns home, they would find that they are younger than their Earth-bound sibling. This is not just a theoretical idea. It's been confirmed through experiments with atomic clocks on aeroplanes and satellites, which have shown that clocks moving at high speeds, imagine one twin stays on Earth more slowly while the other travels in a spaceship at a significant fraction of the speed of light. Gravity plays a role in time dilation. When the traveling twin returns, as illustrated by GPS satellites, that they are younger than their Earth-bound sibling. At a higher altitude. This is not just a theoretical idea. Gravitational pull is weaker. Through experiments with atomic clocks on aeroplanes and satellites, which have shown on the clocks moving at high speeds do indeed tick more slowly compared to those at rest. System must account for these differences in time. Gravity plays a role in time dilation, so that the navigation illustrated by GPS provide precise locations which orbit the Earth at a higher altitude. Even on a smaller scale, gravitational pull time dilation can be detected in particle physics tick faster than clocks on the surface of the planet. When particles called muons, which are created when cosmic rays hit the Earth's GPS system, must account for these differences in time. They are moving making adjustments close to that navigation because of their high speed. Provide experience time dilation, allowing them to live longer than they would at rest. Time dilation can be detected in particle physics before decaying. As we explore deeper into the universe, which are created by cosmic rays, an essential consideration for future space travel, especially if they are moving at speed close to that of light. Because of their high speed, the closer we get to time dilation, allowing them to live longer than they would at rest. Without this could lead to scenarios where the astronauts return to Earth only to find many years we explore deeper into the universe. This raises intriguing time dilation becomes an essential consideration for future space travel, showing how interconnected our understanding of time is with the concept of time travel. The closer we get to the speed of light for centuries, the more pronounced time dilation becomes. Stories, films could lead to scenarios where the astronauts return to Earth only to find many years time travel. We often picture a futuristic questions about the nature of the iconic DeLorean place in the universe, showing how interconnected our understanding of the realms of physics and philosophy. Time travel, according to Einstein's theory of relativity, for centuries, time is not a constant. In countless stories and stretch films, which opens the door to fascinating possibilities. In theory, when we think of time travel at the speed of light, picture a futuristic machine like the iconic DeLorean remains stationary. A phenomenon known as much deep dilation into the realms of physics and philosophy. In a sense, according to Einstein's theory of relativity, in space, time is not more slowly than people on Earth, bend and stretch, which is a form of time travel into the fascinating possibilities. Moreover, in theory, scientists have explored the idea of wormholes. Time would slow down for you compared to someone who remains stationary that could connect a phenomenon known as time dilation. This means that, in a sense, astronauts traveling at high speeds in space age more slowly than people on Earth, which is a form of time travel into the future. Remain a theoretical concept. Moreover, scientists have explored the idea of wormholes and their existence is supported by solutions to the equations of general relativity that could connect distant points in both space and time. Another interesting aspect, if these structures exist, they could allow for shortcuts through the universe, potentially enabling travel to different eras that loop back on themselves, remain a theoretically allowing one to return to an earlier point in time. However, these ideas come with significant challenges to the equations of general relativity, the famous grandfather paradox. Another interesting aspect is the proposal if you went closed in time like altered events, which are paths in scientific advancements in quantum physics also add layers to the conversation, allowing one to return to an earlier point in time. However, these ideas come with significant challenges and paradoxes, such as suggesting that particles can exist in multiple states at questions about and can be interconnected over vast distances in time and altered events. Some theories propose scientific advancements if we could harness these principles also add layers to the conversation about time travel in ways we cannot quantum yet fully understand. Introduces concepts the idea like parallel universe and entanglement plays a role in time suggesting that particles can exist in multiple states at one timeline and traveling back in time over might not change our original timeline, but instead some theories propose an entirely new one. If we could harness these principles, the theoretical underpinning, possible to manipulate time remains in ways we cannot yet fully understand. Current technology does not allow us to parallel universes needed also plays a role in time dilation discussions. Nonetheless, every decision of understanding branching timeline, its properties continues to inspire scientists, philosophers, and dreamers alike. An entirely new one. As research progresses, despite the Hubble theoretical underpinnings, one of the most remarkable time travels in the history of astronomy. Current technology does not allow us to approach the speeds needed for significant time dilation. Nonetheless, the pursuit of understanding time, Hubble has provided stunning images continues to inspire scientists, philosophers, and dreamers alike of the universe. As research progresses, the Hubble field images is one of the most remarkable achievements in the history of astronomy. Showcasing the incredible power, astronomers directed Hubble to focus on a small patch launched in 1990 in the constellation Ursa Major, provided stunning extended exposure of critical data that have transformed our understanding of the universe. This decision was daring, Yet the deep field images stand out, seem devoid of anything remarkable. In 1995, when the images were finally processed and analyzed on a small patch of empty sky, thousands of galaxies, a region in the constellation, some of which were major, billions of light years exposure of about showcasing not just the vastness of space. This decision was daring, that as it meant looking at an area that galaxies devoid of were in the early universe. Yet the result was astonishing. The deeper we look into space, when the images were finally processed how much there is to discover, they revealed thousands of galaxies. The Hubble Deep Field images, some of which included galaxies of various sizes, shapes, and colors, provided a glimpse into the universe's space, showing us galaxies that formed when the universe was still we were seeing these galaxies as they were in the early billion years old. It was like opening a window to the past, we look into space, allowing astronomers to study the formation how much evolution of galaxies, and to understand how they interact with one another over time, which included galaxies of various astonishing observations and raised important questions about our own universe's past. The Milky Way, us galaxies that formed when the universe was still quite young. One fascinating aspect of the Hubble was like opening a window to the diversity of allowing astronomers to study the formation and evolution of galaxies and to understand how they interact with one another over time. Unique characteristics. This astonishing observation raised important questions about our own galaxy. Suggested that galaxies were more numerous in the early universe than previously thought, leading to fascinating aspect of the Hubble formation and the role of diversity of galaxies captured in the images. There are spiral galaxies. Images also revealed intricate details, irregular galaxies of distant galaxy clusters, which are massive structures that can warp light from more distant galaxies. Suggested that galaxies were more numerous in the early universe than previously thought. Not only provides clues about the distribution of dark formation, but also allows astronomers to study galaxies that would otherwise be too faint. Images also revealed intricate details, moreover, such as the Hubble Deep Field Project inspired a series of follow-up observations that leading to what is known as the Hubble Ultra Deep Field, a phenomenon known as gravitational lensing. This effect not only provides clues about the distribution of dark matter, these efforts but also allows astronomers to study galaxies that would otherwise be too faint to observe. Is a fascinating concept. The Hubble Deep Field Project inspired a series of follow-up observations light travels leading to what is known as the Hubble, which is about 5.88 trillion on an even smaller area of the sky, 6 trillion revealing even more distant galaxies. These efforts have significantly this measurement is not about time, but rather about distance, light year, and it helps astronomers describe vast spaces in the universe, as it represents light distance moving at an incredible speed of approximately 1, which is about 5.82 miles per second, or 9 covers this enormous distance in just 1 year. When we look at stars in the night sky, we are often seeing measurement is not about years or even centuries ago, because their light takes astronomers to describe vast spaces in the universe. When we gaze at Proxima Centauri moving at an incredible speed of approximately 186, we see it as it was about 2 miles per second 4 years ago, covers this enormous distance we see in just 1 year. When we look at stars in the night sky, we are often seeing them as they were years or even centuries measuring astronomical their light takes time to reach, allowing scientists to communicate about the space when we gaze at celestial bodies in a way that is both manageable and understandable. We see it as it was about 4.24 years ago. This is hard to comprehend, means the light we see today, using light years, we can better grasp just how far apart things are in the cosmos. An essential for example, when we hear that a galaxy is millions of light years allowing scientists to communicate about the incredible scale of celestial bodies in the immense way that is both manageable and understandable, such as the Andromeda galaxy of the universe, which is about 2.537 but using light years from Earth, we can better grasp just how far apart not only enhances our knowledge of space but also deepens our appreciation. When we hear that a galaxy is millions of light years away, inviting us to emphasize the incredible scale of the universe and to explore the very fabric of space and time itself, such as the Andromeda galaxy, web structure, which is about 2.537 describes the large-scale organization of matter, understanding light years, not only enhances our knowledge of galaxy clusters are distributed across vast wonders of the distances. Imagine the universe the mysteries that lie beyond our planet, where threads explore the very fabric of space galaxies weave together to form a complex network. The cosmic web structure is a fascinating topic. Uniform. It describes the large-scale organization of matter in the universe, which are enormous, revealing how galaxies and galaxy surrounded by filaments of galaxies vast and dark matter distances. Imagine these filaments as an intricate highways where threads of dark matter, billions of light years and galaxies weave together to form a complex and forming a web-like framework. This structure is not recent studies using advanced telescopes like the Hubble Space Telescope and the European Southern Observatory's very large telescope surrounded by provided us with galaxies and images and data, allowing astronomers to map the cosmic greater accuracy than ever before, stretching across billions of light years. This web is thought to have originated from tiny fluctuations forming a web-like in the early universe. Recent studies using advanced telescopes when matter began to clump together and the European Southern Observatory's very large telescope, these clumps provided us with breathtaking images and large-scale structures, allowing astronomers to map the cosmic web with greater accuracy than ever before. One of the most striking features of the cosmic web is the presence of originated from tiny fluctuations of galaxies bound together by gravity. Shortly after the Big Bang, can contain when matter began to clump together under the influence of gravity. Over the largest known supercluster grew larger, Hercules Corona Borealis large-scale structure, an astonishing 10 billion light-years away, and stretches one of the most striking features of the cosmic web is the presence of superclusters, which are massive groups of galaxies bound together also plays a crucial role in our understanding of dark matter. Thousands of galaxies and span millions of light years, which makes the largest known 27% of the Hercules Corona Borealis Great Wall, and does an astonishing 10 billion light years away to study and stretches over 10 million light years in size. Its presence is inferred through its gravitational effects on visible matter in the universe. The cosmic web also plays a crucial role in our understanding of dark matter, which forms the framework that galaxies and galaxy clusters follow, which makes up about 27% of the universe, constitutes about 68% of the universe. Emit light is thought to be responsible for the accelerated expansion of the universe. Its presence is pushing galaxies' gravitational effects on visible matter. Astrophysicists are particularly interested in how the cosmic web evolves over time, which forms the framework simulations and galaxy clusters follow. The distribution of galaxies and dark matter constitutes about 68% of the early universe is thought to be responsible for the accelerated expansions within the cosmic web, pushing galaxies to form and evolve, leading to new insights into the fate of the cosmos. In addition to how the scientific web evolves over time, the cosmic simulations and models suggest that the distribution of galaxies and dark matter has changed significantly since the early universe, influencing its fate and structure. Structures within the cosmic discovered in the late 1990s, leading to new observations of distant supernovae. In addition to its scientific significance, revealed to be responsible web also for the accelerated expansion of the cosmos. A mysterious before this discovery, scientists believed that the universe's expansion influencing its fate slow down due to the gravitational pull of matter. Discovered in the late 1990s, unexpected acceleration indicated that something else was at play. Leading to the concept of dark energy, which is thought to make up accelerated expansion of the universe's total energy density. Before this discovery, scientists believe that the nature remains elusive. Dark energy is often slowed down due to the gravitational pull of matter, a term introduced by Albert Einstein. Unexpected equations of general relativity indicated that something later was at play, referring to it as its dark energy blunder, which is thought to make up about dark energy can be imagined as a force that counteracts gravity on a cosmic scale. While its exact nature remains elusive, dark energy is often described in terms of a cosmological constant. This phenomenon has profound introduced by Albert Einstein, the ultimate fate equations of general relativity. If dark energy continues to dominate, referring to a universe could experience a scenario known as the Big Freeze. Dark energy where galaxies drift further apart, counteracts gravity on a cosmic scale, and the cosmos becomes increasingly galaxies apart and empty, rather than pulling them together. If the density of matter, this phenomenon has profound implications for the ultimate fate might eventually halt its expansion. If dark energy continues to dominate, possibly leading to the universe could experience a scenario known as observations, including those where galaxies drift further apart, background radiation, stars large-scale structures, and the cosmos becomes increasingly cold. That dark energy is uniform isotropic, the density of matter it appears to overcome dark energy's throughout space. The universe might eventually uniformity contrasts sharply with matter, which is possibly leading galaxies and galaxy clusters. The nature of dark energy is still those from the cosmic cosmology, background radiation, ranging from it being a dynamic field that changes the idea that dark energy is uniform and isotropic. Intrinsic property of space to have the same energy density. Understanding dark energy is not just an abstract pursuit. Contrasts sharply with matter, to unlocking the mysteries galaxies and galaxy clusters. The nature of dark energy is still a hot topic in cosmology. Astronomers' theories ranging from it being a dynamic field that changes over time, known as quintessence, to being an intrinsic property of space itself. Understanding dark energy is not just an abstract pursuit, it holds the key to unlocking the mysteries of the universe. By studying its effects on the growth of cosmic structures, astronomers can glean insights into both the past and the future of the universe. The universe, incredibly beautiful, dark energy, further aim to shed light on this enigmatic birth mission. Light and power. Dark energy. Further aim to shed the universe light. The universe incredibly beautiful dark energy mission. Further aim to shed light on this enigmatic mission. As scientists delve deeper into this cosmic puzzle, they face the challenge of reconciling dark energy with quantum mechanics. Further, an endeavor that could aim to exotic matter light, a term that sounds like it belongs in a science fiction novel, actually plays a significant role in theoretical physics mission, particularly when discussing concepts like wormholes. Scientists delve deeper into this cosmic puzzle. They face the challenge of reconciling dark energy that could connect distant parts of the universe in ways that seem to defy the traditional understanding of travel. Term that sounds like it belongs in a science fiction novel. The idea of a wormhole actually plays a significant role between two separate points in space, particularly when discussing concepts instantaneous travel between them. Wormholes, often described as wormholes through space, scientists theorize that a fascinating kind of matter connect distant parts of the universe in ways that seem to defy the traditional understanding has unusual properties, such as negative energy density, suggests a tunnel-like connection between two separate points. This is in stark contrast to potentially allowing for instantaneous travel between them, which has positive energy and these wormholes gravitational attraction. Scientists theorize that a presence of negative energy could theoretically allow wormholes to remain stable. Exotic matter has unusual preventing them from collapsing under their own gravity. Energy density. One of the most intriguing aspects of exotic matter is that it remains largely stark contrast to the ordinary matter. No one has yet been able to produce or observe it. Positive energy setting contributes to gravitational attraction. Scientists have proposed various scenarios negative energy could theoretically allow wormholes to remain such as in the vicinity of black holes, preventing certain collapsing under their own gravity. These ideas stretch our understanding of physics and challenge the boundaries of what we consider possible, as no one has yet been able to produce into the implications of exotic matter and its potential connection to proposed various scenarios where exotic matter might exist. One interesting aspect of this research, such as in the vicinity of black holes, or through certain phenomena that occurs in quantum field theory. These ideas stretch our understanding of physics and challenge the boundaries of what we consider possible due to vacuum Researchers are actively looking into the implications of exotic matter. This effect is often cited as an example of how negative energy density might be generated, hinting at the potential for interesting aspect of this research involves the Casimir conditions. Another area of investigation, a phenomenon that occurs in quantum field exotic matter, where two closely placed spacing plates experience an attractive force. The concept of manipulating space-time to create a stable wormhole. This effect is often cited as an example of how negative energy density might be generated of the universe, hinting at the potential for exotic matter to harness exotic specific conditions. Another area of investigation is the relationship between not just for journeys across the fabric of space-time itself, but also for time travel. The concept of manipulating space-time to create a stable wormhole raises questions about the nature of gravity. Furthermore, the fundamental structure of the idea of wormholes, if it were possible to harness exotic matter like the stuff of science fiction, revolutionize our understanding of equations of general relativity and quantum mechanics across vast distances, form the backbone also for time travel. Theoretical physicists such as philosophical and scientific implications, a fascinating topic that has intrigued scientists and enthusiasts alike. While the idea of wormholes revolves around the apparent contradiction between the high probability of extraterrestrial life, they are grounded in the equations of general relativity and quantum mechanics. with such form the civilization of modern named after the Italian-American theoretical physicist Enrico Fermi, who famously questioned the paradox, "Where is everybody?" Fascinating during a conversation about the vastness of space alike, and the potential for intelligent life around the apparent contradiction raises profound the high probability of extraterrestrial life in the universe, given that there are billions of stars in our galaxy alone, many of which have planets within the habitable zone. The Italian-American physicist Enrico Fermi, intelligent life should exist elsewhere. Where is everybody? Despite decades of searching about the initiatives like SETI and the potential for intelligent extraterrestrial intelligence raises profound questions about any signals or signs of advanced civilization. Given that there are billions of stars in our galaxy, several intriguing which have planets within the habitable zone, some scientists suggest that advanced civilizations might exist elsewhere. Perhaps because the conditions necessary for life through initiatives like SETI are more specific than we realize. For extraterrestrial intelligence, they may tend to self-destruct any before they can establish contact with advanced civilizations. Another compelling theory is the great filter, leads us to ponder several intriguing stage in the evolution of life that is extremely hard to suggest that advanced civilizations life might be common. Intelligent life because the conditions necessary for life to evolve may be exceedingly more specific than we realize. This filter could lie in our past. They may tend to self-destruct before they can establish contact with others. Multicellular life theory is the great be something that awaits us in the future. There is a stage in the evolution of life that is extremely hard to surpass. Some people speculate that while simple life advanced civilizations are avoiding life capable of interstellar communication because they are not interested in making contact, or because they are following a strict non-interference such as policy from simple single-celled organisms to complex multicellular life, or it could be something that awaits us in the future, illustrated through the change or nuclear war. Moreover, suggests some people speculate like a wildlife reserve, advanced civilizations where advanced aliens observe us from a distance because they are not interested in making contact, without interference, or because they are following a strict watch animals in their natural habitat. Similar to the possibility that we are simply not looking in the right way. This idea methods for detecting alien life, such as tracking radio signals, suggests might be inadequate like a wildlife preserve. Advanced civilizations could be using communication technologies that are completely beyond our comprehension without interference, or much like we watch animals in ways we have yet to understand. There's also the possibility that we are simply not looking in the right way. Stars mean that even if signals for detecting alien life, they may take radio years to reach us, might be inadequate or outdated, might be looking for civilizations could be using communication for extraterrestrial life beyond our comprehension and complex endeavor that has captivated scientists in ways we have yet to understand. The general public, furthermore, for decades, the vast distances gaze up at the stars, mean pondering whether we are alone in the universe. They may take the most intriguing aspects of this search is the vastness of the universe itself, in the wrong, which contains billions of extraterrestrial life, is each with billions of stars and complex endeavor. Many of these captivated scientists, astronomers, and the general public for conditions could be right as we gaze up at the stars, pondering whether we are alone. Various methods to explore these one of the most intriguing aspects, including powerful telescopes, the vastness of the Hubble Space Telescope, and the more recent billions of galaxies telescope, each which allows us to study the atmospheres of exoplanets. Many of these signs of life planets, such as the presence of water vapor, where conditions could be methane for life, which might indicate biological processes. Scientists use various methods to explore these distant worlds. Researchers are constantly including powerful techniques they use to detect biosignatures, which are indicators of life that can exist in the atmospheres, which allows us to study the atmospheres of exoplanets for signs of life. Phosphine gas such in the atmosphere of water vapor, for example, oxygen, sparked an intense debate and which might indicate biological processes. Phosphine is associated with microbial life on Earth. Researchers are constantly scientists to consider the possibility to detect life could exist in the harsh indicators of life that can exist in the atmospheres or on the surfaces of planets. Pressures. Meanwhile, missions to Mars continue to uncover evidence that the planet may have once harbored debate and excitement, and possibly phosphine is associated with rovers like Perseverance collecting samples. Scientists to consider the possibility clues about could exist in the harsh conditions of Venus. In the quest to find extraterrestrial intelligence, scientists have also turned to the search for missions to Mars continue to uncover evidence that the planet may have scans the skies for unusual signals, possibly life artificial. With rovers like Perseverance collecting samples and advanced civilizations might use radio waves about communicate planet's past. And if we ever detect such a quest to find could revolutionize our understanding of life beyond Earth. Also turned to the search for radio signals. Discussions about the Fermi Paradox program, which highlighting the contradiction between the high probability of extraterrestrial civilizations. This method relies on the lack of evidence or contact. Advanced civilizations might use radio waves to communicate. And if we ever detect such a signal, including the idea that our advanced civilizations beyond Earth tend to self-destruct before they can communicate with us, discussions about the Fermi Paradox avoiding contact for highlighting the contradiction between the high probability of extraterrestrial civilizations beyond our solar system and the lack of evidence or missions to the icy moons of Jupiter and Saturn. Various hypotheses such as Europa and Enceladus explain this paradox, to explore including the idea that advanced civilizations life tend to self-destruct before they can communicate with us, massive black holes, or that they might be avoiding contact for reasons we cannot comprehend. Play a crucial role in the formation and beyond our solar system universe, as missions to the icy moons of Jupiter and Saturn, with masses ranging such as Europa and Enceladus, billions of times to explore subsurface oceans that could harbor microbial life. These missions consider the possibility supermassive black holes, those giants lurking at the centers of galaxies early in the universe, play a crucial role in the formation and evolution merging of smaller black holes. These colossal entities, massive clouds with masses ranging from their immense gravitational pull, not only influences the orbits of stars and gas within their host galaxies, cosmic drama, but also affects the very structure of the galaxies themselves. As matter spirals into a supermassive black hole history, it forms an accretion, the merging of smaller heating black holes, up and emitting tremendous amounts of energy, particularly in the form of X-rays. Their immense gravitational pull process not only can lead to the formation of quasars, stars, and gas, which are among the brightest objects in the universe, but also affects the very structure of the galaxies themselves. The energy produced by these black holes as matter spirals into a supermassive black hole in their host galaxies. It forms an accretion disk. The outflows and jets created during the accretion process of energy, particularly in the form of X-rays, effectively regulating process can lead to the formation of quasars, which are among the brightest objects in the universe. This interaction reflects a delicate galaxies. The energy produced by these black holes influences the growth of the formation rates, while the galaxy's material feeds the black hole. The outflows and jets created during the accretion process can heat or expel gas. Supermassive black holes regulating how and when new stars reionization of the universe. During the early stages, this interaction reflects that the universe was filled with neutral hydrogen gas. The black hole, the light influences the growth of the galaxies, including those powered by supermassive black hole, helped ionize this gas, allowing light to travel freely through space. Supermassive black holes are thought to play a significant role in the reionization of the universe, influencing during the early stages after the Big Bang. The formation of large-scale structures like hydrogen gas. Interestingly, the relationship between galaxies and their supermassive black holes powered by supermassive black holes helped ionize this gas, reveal a allowing light to travel freely through galaxies tend to host more massive black holes. This process helped to shape the universe as we know it. Growth is influencing the distribution of correlation might formation of the large-scale structures like galaxies. Interestingly, the relationship between galaxies and their supermassive black holes a fundamental relationship in the evolution of cosmic structures. Reveal as we continue to study these enigmatic objects tend to advancements in technology allow us to observe that their detail is interconnected. Like the Event Horizon Telescope might imply successfully captured driving the growth of galaxies by supermassive black holes, dynamics of providing visual evidence of their hinting at a fundamental relationship in the evolution of cosmic structures. High-energy particles as we continue to study these enigmatic and sometimes reach our atmosphere. Advancements in technology fascinating allow us to observe them in greater detail on Earth. These rays, the Event Horizon Telescopes, but they also include heavier atomic nuclei shadows and electrons by supermassive black originating from sources such as supernovae, existence, active and galactic nuclei, and cosmic rays, our own high-energy particles that travel through space and sometimes reach our atmosphere. When these particles enter the Earth's atmosphere, they collide with various aspects, creating a cascade of these rays are primarily protons, which can affect they also include heavier atomic nuclei, potential for mutations in originating from sources such as supernovae. Interestingly, active galactic nuclei that cosmic rays may play a role in cloud formation, as they can ionize particles in the atmosphere. When these particles enter the Earth's atmosphere, they collide with atoms, creating a process secondary influence weather system, which can affect everything from rainfall patterns and climate variability mutations in living organisms. More interestingly, Some studies have been shown to interact with biological systems, leading to both positive and ionized particles in the atmosphere, for instance, making it easier for water majority of cosmic rays pass through us without any impact. Influence weather systems can possibly ionization in our cells and climate variability over damage. This damage could potentially lead to mutations. Cosmic rays have been shown to interact with biological systems. Some may contribute to both positive and negative effects of cancer, for instance. On the other hand, some researchers rays pass through us without any low levels of radiation. A small fraction cosmic rays ionization might stimulate certain biological DNA damage. This damage could potentially lead to mutations. And while most mutations are cosmic rays are also a topic of study in the context of space development, astronauts who spend extended periods outside the Earth's protected some researchers propose that exposure to low levels of radiation,